Здоровенькі були. Це дуже приємно зараз бути у Києві та трохи спілкуватися українською. Це вже не робив майже 5 років. Так, але ж ми мусимо це робити англійською мовою, да? Okay, so I'll switch to English. So, very, very happy to be here now in Kyiv. In this very foggy Kyiv, as I remember it. It's always fogs like this happening in November. And it's, oh, that's not mine. Once again, very great to be here. It's fully packed. I'm impressed. Thank you for being here. So a few words about me. I'm Dmitry Aleksandrov. I work for T-Systems. I'm also part of the co-lead of the Bulgarian Java user group. And proud to be a chief architect there at T-Systems and honored to be a Java champion of this year, also developer champion. Some, thing to share with you. We are quite happy that our Java user group has won this year Duke Choice Award. So I think that here in Ukraine you have a wonderful Duke. Just keep on going and you will have this award. A bit disclaimer before start. You have heard the GPU, but there will be no Bitcoin miners here. Okay, how many of you remember this thing? Aye, we're almost the same age. And how many of you remember this thing? Yeah, you see, this is the view of happiness. When I was, about, 12 years old, I've got this on my screen and I was, shining, yeah. It's so much cool, and we're going to play some really cool games right now. So today we're going to talk about Java and the GPU, and a good way to do this is to start with the definition. What is a video card, actually? So just another disclaimer here. So before, going into details, I really have to make some, prehistory of what is a video card and how can we use it. Just because without it will be a little bit, complicated to dive in Java topics. So as you probably see, this was stolen from Wikipedia. So video card is a piece of hardware which converts your bytes into memory to some analog signals and sends it to the display. But we are in 21st century, and most of the time the signals go digital. So and there is not only sending the signals from your memory to your video card, there is also a big processing. So current video cards are quite complicated. Most of the time, you just say to the video card, okay, please render me an image with this quality. I'll send you the frame, just render it, make a beautiful image, and just don't keep me bothering. And the video card does this for you. And currently, the video card may be one of the most expensive parts of your system. Yeah, actually, even more expensive than a processor even. So, and probably you have heard talk about the GPU. So what may be a GPU? Let's start with the definitions as well. So this is a graphic processing unit. Actually, the first use of this word is back in 1999, and it was with the GeForce 256 called the world's first GPU. How many of you have had it? I have it, I had it. Yes, as I received it, I was, shouting loud. So most of the time, Nvidia defined it as a kind of a single chip processor, a specially dedicated processor for, transforming lights, triangles, polygons, and so on. It's also a special piece of hardware just to work with your graphics. And it had the capability of transforming out 10,000 polygons per second. Well, ATI, how many of you remember ATI, Canadian company? Hey. How many of you are 1985 or something like this? Yeah, born 1985. Okay, so a few of you, but you still remember this, okay. So ATI called it VPU, but that was, never used. So most of the time, video card, as I told, is a special piece of hardware that schematically looks like this. You have some fancy stuff like shaders, shader cores, texture cores, rasterizers, something very special dedicated to video cards. But then at some point, we came to the idea not only graphics can be processed in video cards, and here we have this idea of the general purpose computing on graphic units. So it's called GPU. So as I said, not only to perform graphic calculation, but somehow to float the things of the CPU you have to the video card. And since we have a piece of hardware which can, do some stuff for us, we have to use it. It looks cool. Let's look at the hardware, actually, how it works. So processing. So processing most of the time is done on a processor. So the processor, the CPU schematically looks like this. So to make some calculations, you most of the time have to fetch, decode the data and the instruction, move them to the arithmetic and logic unit. Well, you actually execute these calculations. For that, you have the contexts, like, for example, all the registries are there, everything supporting your calculations. But then you have a lot of other units which are quite fancy. So first of all, data cache. So that's a big piece of hardware because, we usually process the same data or the same pieces of data or nearby pieces of data, and here we can accelerate this stuff. But since our processor most of the time, can be interrupted and can run, simultaneously many programs, we have another fancy units like, branch predictors, like out-of-logic controllers, prefetchers, everything to accelerate. So, but do we need everything this for graphics processing? Actually, no. So let's simplify. For the graphics, since we actually most of the time works with arrays of data, we know very good what is the next data we're going to process. Just remove all the things. Make a processor really stupid. So we need only fetch, decode, ALU, and some context to make it run. And since the processors are very, stupid, they are very cheap. So since they're very cheap, we can put a bunch of them just because the nature of the graphics processing is parallel. So we have an array of data, a big array of data, and we are able to process it simultaneously. They are not, so every pixel is not connected to the other pixels. So put a lot of stupid processors on a silicon board. But probably most of you have heard that on graphics as well. So we are processing most of the time the same instruction over different sets of pixels of data. So here comes the idea of the SIMD paradigm. So have you heard of SIMD? So single instructions, multiple data. So I won't dive into details. You can always get me on the lunch. Oh, we have lunch after that, my God. So after that, I will tell you more information about it. But since the idea of SIMD is that you have an instruction and you put it on multiple data, and it just, accelerates. So in one tact, you do multiple processings. So if we combine these two ideas, we can make our processor even simpler, because then we have only one fetch decode block, a lot of arithmetic logic units, sorry for that, and some contexts. So as I told you, if you use SIMD paradigm, we can just take the bunch of pixels, apply some instructions on them, and receive a result, another bunch of pixels. So now if we combine two of these ideas, like many processors which are quite stupid, and apply this SIMD paradigm, look what we have. So we have a very, very powerful multi-threaded, I would say, multi-core machine that is specially dedicated for processing of the graphics, but it's a lot of processing power, although the processors are quite stupid, let's be honest. But there are a lot of them. Okay, so we should code that, because we have this power. We've got the power. And how on earth can we do this? So, it all came from the gaming industry, of course, and some cool video cards that were able to float some of the tasks from the CPU to the GPU, to the video card, to make some beautiful effects. But most of this effects were kind of hard-coded. How many of you have played not CS as computer science, but as a Counter-Strike? Counter-Strike. Yes, Counter-Strike. You've seen the water there, the water effect. There was some strange water effect there. So this water effect was kind of hard-coded as an algorithm. It was considered as a standard, and we developers, as coded the games, we actually just called it, okay, apply this wonderful effect to this area of the screen, and video card will do the rest for you. Well, if your video card is stupid enough and cannot do this, sorry, then you don't have beautiful water. Okay, so of course, not everything can be hard-coded. And you know, good vendors like Nvidia, like, you know, the same ATIs with Life, opened access for the developers to code, to somehow code on these quite stupid processors, and they gave us the ability to run some small programs on these stupid processors, on a bunch of these processors. And these programs were called shaders. So most probably you have heard this word. How many of you are modding their games? I mean, modding, giving some, you know, downloading some stuff and say, okay, now if you download this stuff, the game will be cooler. So most of the time you download shaders, and these shaders are programs that produce some more fancy effects. Like, for example, when you shoot somebody, there will be a lot of blood happening there in the CS. And it's done on the video card. So we shoot, and then video card produces a lot of blood. So these are the shaders. So first of all, these shaders were, you know, different for geometry, for pixels, but then actually they became common program. And you see, by the way, is there somebody who cannot see it from me? Should I hide somehow? Okay. So we've got these shaders. They are now kind of small programs for doing something with these processors. And of course, there were several languages for writing shaders. So maybe the oldest one is Random Man. Some of you, how many of you have coded on a video card? 2 people. You can leave the room. Okay. But there were, you know, languages like Random Man, like, you know, DirectX, ISM, the most used one. HLSL is also quite famous. But so mostly these programs look like this. So they're kind of a C-like programs. If you take a look on the left, you see some very C code, CLI code, which actually this is code to transform a pixel, which is then compiled, like we know we are using, you know, to run processors, the same processors. So we compile this code for this architecture for this processor, and we got this assembly code. We actually get one pixel and does something to this pixel. Cool. So most of the time, it was used to bring some beautiful effects, of course. You see the picture on the left is not as much good as this on the right. So you may say there's so much low level. Yes, you're right, absolutely right. But it all started with gaming, as I told you previously. So there was a set of you know, abstractions made to this thing. So like, of course, you've probably heard of OpenGL and DirectX. Every time you install a game, the next step is to install something called DirectX. It's obvious, yes. So these were a set of abstractions which opened access for the developers to access low-level stuff on a video cards, or to make, you know, some upper-level abstractions, like, for example, draw me something fancy, and I will do the rest. I will write the shader for you, or create some, you know, something to run on a video card. It all started from this, and since it's a Java conf, or it's not exactly Java conf, Devoxx is not exactly, but mostly Java conference, how on earth can we do it on Java in terms of graphics? So of course, Java said, cool, there's an OpenGL, we have to use it. So there was a GSR back in 2003 called 231. Which, you know, said, okay, but why on earth should we use graphics on Java? Yes, we don't write games on Java. Java is a virtual machine. It's not, so much. Java is very slow, they say in 2008. And since they say 2008, they say, okay, we don't need this standard anymore. So it actually left its life in terms of JSR in 2008. But there is a project called GeoGL. It still lives as a separate project. And we are able to access all this OpenGL stuff via glue and glut. So it's a kind of a binding to the language. So let me show you a small called BASIC in school. What was the first thing you've ever done? That was a screensaver. You draw a fancy line on a random with random color, and it's beautiful, yes. So here you can make almost the same. This is a Java code. I will make it a little bit more. So it's a Java code. And if you run it, so we are now producing some not very typical for an enterprise developer stuff, like this beautiful picture. So we're writing code in Java, then it somehow connects to the OpenGL level on our machine and produces this image. We do not control much of the video card here, but we're able to do some stuff which is not typical for Java, like draw triangles. And it's impressively, but it works even on this Mac. So, and you will be surprised how code Java I created this. So this is not me, the guy said. So he created Minecraft. This Minecraft was written exactly with this GeoGL stuff over some library. But we are not game developers, or maybe there are some game developers, but sorry for that. Me personally, I'm not. So we have realized we have a bunch of power we want to use. And there was this attempt -1, I call it. So the vendors of video card have opened access not only to the video cards, like you can put some shaders inside, but you can read also the frame buffer programmatically. So the frame buffer is the results of the resulting image actually before it goes to the monitor, it goes to the frame buffer. So since we are able to access frame buffer, why don't we just, take our data and code it as a bitmap image, a usual bitmap image. So it's an array of data. So bitmap is array. We can encode not only colors, but any data we want. And write some shader and transform this bitmap image to another bitmap image with our video card. And read it back from the frame buffer. So that was my attempt back in 1999, actually, I've done it. So I've taken an image, wrote some shader. It crashed, of course. First of all, it crashed. It has no debug. So if it crashes, you just, reboot your computer and see what's wrong. You actually do not see what's wrong. You try something else until it's not, rebooting. And then I was able to take an image, to write a shader, and to transform it. So I first used a video card, which was kind of cool. But some guys in Stanford University said, okay, this is not a civilized version of using, GPU. Let's make an infrastructure. So they've made an infrastructure called Brook GPU, which actually provided us access a small, subset of ANSI C, which was able to be compiled in and stuff readable by GPUs. And it all actually automated all of this reading from buffers and taking it back. So Brook GPU was the first attempt to make it. But of course, people say, okay, we have a bunch of power. Let us try to use it. So Microsoft said, okay, we need direct compute. AMD say, we will provide you with this resource on FireStream, OpenACC, and probably now other buzzwords. Nvidia said, we will make CUDA. How many of you have heard of CUDA? How many of you have used it? Okay, good. And then they say, but we need a more wide standard called OpenCL. So OpenCL, Probably heard of it. Cool. Nice. So I made it bold just to say we will focus on these two technologies. So, and once again, why Java and the GPU? This is the obvious question. As the guys from the first session, Barik and Evgeny said, why on earth should we use this technology? Yes, Java is slow, it's not graphics. But Java is safe. It runs on 3 billion devices. If you install Java, you have this wonderful banner. It runs on 3 billion devices. And Java now runs not only on, doing something with our browsers, but it's very much used in data analytics and data science. So everything which is done with banking, for example, with finance and so on and so on, there's a bunch of Java. So a lot of COBOL, of course, but they are migrating to Java. Maybe in 2,500 years, they will migrate back to, well, fully migrate to Java. And so Java is used there. And since there's a lot of analytic work that can be parallelized and done somehow on a GPU, we should use it. So, and to use it, as I told you, we have two of these technologies. But Java is a JVM. It's very low level. How can you actually access it? Of course, you can do it via JNI. So you probably heard of JNI. I shouldn't have to. How many of you have heard of JNA? I think it's a better option, actually. But how many of you have tried JNI in production? You are superheroes. Because we can go crazy there. Absolutely. I've tried it, and it's crazy. And we said, okay, there's some, stuff we don't want to communicate with this JNI because it's fancy and it's crazy and it's undebuggable. So what should we use? And some guys take this, force and made the library called JeoGL. Another said, okay, we will make JogAmp, which actually somehow help us to get access to the OpenCL stuff. And some people say JavaCL, but unfortunately not supported anymore. But we have CUDA, which is another infrastructure. And as a result, there were very, quite a bit libraries written that directly use CUDA, but only with the letter J in front. So they are wrappers of CUDA. If you know CUDA, CUDA provides not only very native access to website, it gives you access to many libraries which can actually provide in a good way the computations you want to make. So it was a wrapper for this. So, but we want to code. And this is why we'll make another disclaimer. So this talk is full of disclaimers. It is hard to work with GPU. It's not just to run your program. You really need to know the hardware you're running. It's not like, for us Java developers, it's a virtual machine. We don't care what it runs to. You have to know your hardware. And it's quite a low level. Let us try it. Let us try it first with OpenCL. As I told you, it stands for Open Computer Language, and it's a consortium, a lot of companies, mostly started by Apple, but even Nvidia is there. So it's a very abstract model. The main idea is that it should run on everything which is able to compute. Everything I mean, not only CPUs and GPUs, it should be possible to run OpenCL programs on FPGAs, on DSPs, on everything which is able to do processing. And most of the time, working with pure OpenCL, I would say pure OpenCL, is like this. You still have a host device, which is actually controlling the process. And then you have the compute device, when you set the data and the program, which you have to run. Then asynchronously, it processes something for you, and gives you back the result. This was a very brief explanation, so another short explanation is this one. So to run an OpenCL program, you have to make all of the steps behind me. Create contexts, common queues, memory buffers, compile your program, which should be run on GPU, chunk your data with anti-range, somewhere back in the end say, okay, please execute, and finally get the results. So, of course, better take a look. For this example, I will use something, called vector add. How many of you have heard the idea, what is vector add? Okay, so I have to explain it. So you have two arrays, two vectors, and we have to make an addition operation, an add operation over two arrays. So we take element 1 from array 1, take element 1 from array 2, and write the sum of this element to array 3. So it's a vector operation, as you say. We'll just make this. As you probably may understand, this operation is very, very parallelizable. I mean, we do not depend on any data. So we can take every two elements of the array and simultaneously multiply them and write the result. And let's do it. Prepare a small program. Card. Let's have a look. Yes, this is the smallest program. I'm not sure if I want to zoom in, but I have to zoom in. The main interesting part here is this. You see this? By the way, this is a Java code here. This all is a Java code. So I'm IntelliJ and I'm doing some Java stuff. This is a Java file. But actually, you may see that this is something like more C looking. It looks like C. So this is the kernel. This is something which will be compiled and sent to the video card. And as you see, I won't go too much into details because we can stay for 2 more days here. This is actually the operation we are doing. So we take one array, its ID, second array, its ID, and we write the results in CID. So this is a very small program. Then we have to make a ceremony. We'll make 10 million add operations on my GPU. And then we will make a lot of ceremony. I also won't go too much into details, but the pure OpenCL way means we have to define the arrays, make some pointers to this array, see our devices, find the device, find the platforms, as it may be run on many other on multiple platforms. We have, for example, 10 or 20 video cards in our machine. We want to use them. Then we prepare the contact, then we actually allocate the memory on the side of the device. Then we send the kernel, and actually we build the program. Well, this is the point where you actually say, okay, execute it on the device. Send this to the device and execute it. And then we just release it. And if everything's okay, I sincerely hope so, we will run this program, okay. And only in 277 milliseconds, we have made 10 million of add operations on a video card on this Mac. Once again, to explain everything will be too complicated, so I won't do this in session, but you can actually ask me later or I'll send you the links. So if you do it in... Yes, it is damn hard. Yes, because there is a code which is Java, there is a special subc of C you have to know, you have the communication between your host device and the video card via memory buffers. You have to send data, you have to communicate via memory, and unfortunately, it's not what you are able to send in Java. So there is the data itself, it's not the same. So basically, you have a very special types of data which you have to convert your data to. And most of the time, you start working with vectors. So vector is exactly for this SIMD operation. So for example, if you have float4 vector and you send it to a SIMD device, it will make 4 operations on a float value in one takt. So this is, you have to think about it. So if you work in SIMD, you have to supply this because you have a lot of benefits there. And they are saved there in a very fancy way. So most of the time, okay, like, if you're following the rules of a processor and we have different types of memory, some of which are very fast, some of which are very slow. Of course, the fast memory is expensive, so that's why we have to think about it. So, and in terms of OpenCL, you really have to understand where you put your data. So if you need a small piece of data which is, recurring, like, caches, you put it in a private memory. So every compute unit has a local memory which is faster value, which is like, operation memory. And then you have a global memory, which are those gigabytes of data when you store your images. So you have to think what you do before chunking your data. And as we say, chunking the data, there is something called execution model you also have to think. I will just say it to you in very few words because as I'm trying to understand this, reading the book, I've reread this chapter 14 times before I understood it. So it's kind of impossible to explain it to you in 20 seconds. So, but most of the time, as we work with graphic, the data we are working in OpenCL is most of the time arrays, because only them we can chunk into some pieces and send to different, cores of the video card. So as we chunk them in so-called work groups. I will try to demonstrate it to you via this wonderful example. So we say we work in two-dimensional arrays. Two-dimensional array is a matrix, for example. So what a video card does, it does a lot of matrix operations. Probably some of you have recognized this is a usual matrix multiplication, done with 3 cycles. This is something we do in, I don't know, in 9th year of school or 10th years of school in programming. So to multiply matrices, you have to perform 3 cycles, actually, included. And in video cards, you have to break this model a little bit. So most of the time, you chunk this is not you who chunks the data. So you say, okay, video card, I have several arrays of data. I want you to find the best way to chunk them into pieces, and send it to your cores. And it's called define an NG range. Why should we do that? Because different video cards can chunk the data in different parts. Some video cards can chunk it in 256 parts. Some can do it in, for example, 5012. That's why I say you have to know your hardware before you chunk the data. So on GPU, our code will look like this. We have only 1 cycle, but then we have some, global function calls like global ID. So we send it to the video card, it chunked the data and said, okay, give me the ID, where am I? And just give me this piece of data and I will process it. So defining an ND range means that you have to chunk your data in correct way for your video card. Once again, if we dive into these details, you see, as I was giving into you this talk, I say, every step left and right is a deep dive. So, so I will just say, you have to know it. And if we take a look at a typical GPU, actually, so this is just an information, we see, let me find a mouse. Oops, sorry for that. Okay. You see this 256, 256, 256 value. It means that this GPU can chunk our pieces of data in 3 dimensions in these blocks, 256 by 256 by 256. And as you see, the processor is, as it is very, well, stupid, only less than a gigahertz power. And this is the idea. So if you take a look at a typical GPU, this is another example. You see, it is not able to chunk our data. It is able to process only a single piece of array, or single dimensional array of 1024 elements, but it has a bunch of megahertz. So if your data is not able to be chunked, don't even think about going to GPUs. You will lose computation power. So let us then short think about some CUDA, and just to say how it is. So it may be easier for Java developers. For those of them who tried CUDA, most of the time you have a C file, or they call it different, I guess, CD or something. When you have a C code with some strange, instructions which are only visible to NVCC compiler, but then you code most of the time with some C routines. So you get a mix of a C code and its personal routines. The funny thing is that in Java it has the same binding, but it's very hard to write. But it has another superpowers. Superpowers means that we have already some libraries which are available to Java. They are wrapped in Java, which are for special types of computations. So, like for example, we have a library for fast frontier transformations. We have sparse matrices, everything about them. We can, for example, offload some image processing to GPU, or there is a new library which is scary. Yes, for me, I tried it. I never understood how it works. Deep neural network library. We can offload our, matrices calculations for deep neural learning to this. But as an example, I will give another different things. Okay, this is now a Java code. And here we will do a random number generator. But this is not just a usual random number generator. So this is a very, very good or very, very random number generator. So it's built on some Russian mathematician sequences called by Ilya Sobolev back in '66. But the main idea is, you see, we just call these functions directly from our code, and we received very good random numbers. By the way, the funny thing is that the first time I demonstrated this code to some Java guys, and they were the producers of online gaming stuff, and they really needed these random numbers, very random numbers, and they say as they included this random numbers generator, which are processed on a video card to make it very random, they said we have a better revenue. Okay, I said, okay, give me 10%. They say no. Yes, but they specially used video cards to process a very, random numbers, not pseudo-random. Everything is pseudo-random, but this is more random than the Java random. So, and as we go back to Nvidia, so it has very common model of data, although a little bit different. So Nvidia has threads. For example, you can run, each of their cores has threads. So unlike OpenCL, which does not provide this possibility, you can run multi-threaded things on a single core. And of course, it has its own memory and so on and so on. But there is another thing you should always think about the memory. So it looks cool that you can process and offload your stuff to the GPU, but it's always like this, that you have to push this memory from your memory, which is the RAM memory, to the GPU memory. So on all of this, it's always connected to copying the data. So in terms of GNI and Java, the GNI actually copies the data from the virtual machine memory to some outer area, as you say. You always have to perform at least 2 copies. So first from out of the virtual machine, and then to the GPU, and then make it back. So you will be surprised. For you run the same program on the processor. By the way, look how fast I switch the computations from CPU to GPU. Okay, we're done. And now if we run the same program, it actually takes almost the same time. So let me check. It's even less than on a GPU. Okay, So why does it happen? It actually happens just because here we do not copy the data from and out of the processor. So it just takes the data, process, and put it back. So I made some more low-level profiles on another machine which is able to do this. The actual processing of an item takes about 1 or 2 milliseconds. But copying it from the JVM to some outer memory and outer memory to the video card, it is slow. You have to think about it. And so if we go further, remember, if we take this matrix multiplication program, and if you know your hardware very good, the same problem of this program, optimized version of it can run into this program. So I first saw it, yes, it's a mother of hackery, yes, of course. And this program ran 8 times faster than the previous program because it utilized the SIMD instructions of a processors. But okay, most of you probably don't want to dive into these details. We don't want to think about these host devices. Well, we only want to offload the data. Can we use the GPU partially? We don't only need it everywhere. Yes, you do, or at least you could. And this is called Project Sumatra. So that was a special JVM project where you actually can offload some of the stuff from the streams processing. If we find the lambda in for each, it tries to find this lambda and upload it to the video card. And it was done together with the AMD over there, so-called HCL architecture. Just a few words about it. So as you understood from this talk, you always have to copy the data back and forth. AMD said, we have to optimize it. And so they have created some kind of LLVM language for CPU, which, transformed our GPU code in some LLVM. LLVM probably, heard of it. Well, if you didn't hear about, Google it, it's cool. So it's not exactly bytecode, it's a pseudo bytecode, very low level. But in terms of Java, so most of the time it finds a for each block, it finds a lambda inside of it, and say, okay, we have a bunch of this lambda, streams of this lambda. We can massively parallelize it on our GPU. It sends this lambda to Graal compiler, just-in-time compiler. You have heard of Graal, probably all of you. If not, there is a Chris Tallinger talk later this day. He will tell you more about it. It compiled it not to the bytecode of Java, but to these HCL codes and sent it directly to the video card. And then it was executed on a video card. And together with it, AMD actually tried to solve many problems with this architecture, with this, Project Sumatra. They didn't want to make these copies from system memory to GPU memory, so AMD APUs running on Project Sumatra were extremely blazingly fast, just because there was no memory copy, as I told you. So the GPU just accessed, so was it just pointer mathematics? They just access the memory they need to access, and that's it. So that made it very, very fast. Unfortunately, it all depends on what we are using. So it was not mainstream at this point, and it didn't go that far. So if we want some more general solution, IBM, for example, patched their JVM once again to search for parallel blocks. You don't have to make anything yourself. You need to install just the IBM JVM patched for GPU. And every time it searches, it finds the word parallel. It converts the lambda inside of it to a CUDA code. So you have a big enough n number, big enough just because you don't want to make copies from memory and back to the GPU. And the lambda itself is simple enough, mainly consisting, unfortunately, of primitives. It can be offloaded to GPU. So they made a lot of very interesting optimization for this stuff. And as a result, probably you have heard, so there's a Spark framework. If you enable GPU on it with IBM virtual machine, you receive a huge gain of iterations, as they say. Okay, so you get a lot of iterations which can be offloaded from Spark stuff. So just check this GPU enabler, so it's available for you. But you know, we are not exactly GPU or I would say Java coders. We are enterprise coders. We don't want to think about this. We just want to code it only in Java. So can it be automatically converted without actually thinking? Is there a way to do this? And actually you can do it via so-called API. So it stands for a so-called a parallel API. It's my own improvisation calling it, okay, it works like a Hibernate for databases, it works like a Hibernate for GPUs. So it dynamically converts the JVM bytecode on a host and device code. You don't have to think about it. And the beauty of it is that it uses OpenCL undercover. That means that OpenCL run on every possible hardware. You don't have to think about it. It's very smart. It's very, you know, Spring-like. You don't have to make all of this, you know, fancy, smallest, as you saw, the smallest GPU code for Java. You don't have to make it. It's very easy. So it was once again started by AMD, of course, abandoned. And then AMD said, okay, just make something with it. And it's now back to life. So finally, the same code as we wrote for the 10 million computations, as you saw, all this, you know, I would say ceremony for making, you know, arrays, datas, and so on and so on. This is the same program running API API. So let us explore it a little. Sorry for that. So you see, let us do some, you know, the same vector arrays. So we got one array, two array, and we have to make a result. As you see, or you probably don't see from the back, so I will zoom. This kernel looks very much like this C program which we wrote there. But you don't have all of this, you know, fancy preparation to do this. And if you do this in Java, so let us just run it, you will receive the same computation. Here I get a little bit less on a GPU. This is the same, but run only in Java. We can do some more fancy stuff. I really enjoyed this, this example which they actually gave us. Which is so-called n-body problem. By the way, the cool part of it, that it actually nicely corresponds, nicely cooperates with OpenGL. So if you need to draw something, it won't leave GPU. So okay, you say process this on GPU, don't get it back to Java, just draw it on some board. So you see, this is an n-body program. N-body problem means that you have a body with a gravity, and every particle of it, you know, have to check its gravity against other particles and calculate its way. So we have about 8,000 particles and a beautiful frame rate about 50 frames per second. And it's now down on my GPU. Actually, my GPU is here on the right, and it's very hot right now. I can feel it. Yes, from here. If we done it on a processor, we will receive about one frame per second. So every particle runs on a special kernel, calculates it. We have a bunch of calculating cores. And now you see it's drawn beautifully. So you have this type of calculations. That will be cool. So I personally enjoy it very much. So API is there for you. You can actually try it. minutes left. And of course, what about the clouds? This is a typical paradigm. Everything runs in the clouds. If it's not in the cloud, nobody will buy your software. So, and Nvidia is a very good friend of us, as it somehow created this wonderful technology called Nvidia Grid, which is a way to virtualize our GPUs and provide them from the clouds. So they have created several, hardwares which can be chunked into virtual GPUs. As you see, for example, M60 can be chunked into 32 virtual GPUs. That means we can easily run them in the clouds. So I made a demo. Amazon machine, EC2 machine. I have an instance with a GPU inside, so I'll just run it, especially for you. I wanted to run it on a just before the talk, but you see, it's now about $1 an hour. So it's not like this millicents per hour, but it's now $1 an hour, but it's getting lower and lower as a price, every time it goes. So every year, the first time I did this demo, it was about $4 an hour. Now it's $1 an hour. Now many of these machines are running on less than $1. There is some providers giving you GPU stuff for even I would say 10 cents per hour. So if we connect to this machine, it's running. Please turn off all of your devices. I need all of the internet in the world right now. It's an RDP connection. Yes. Okay. We're not done yet. We're not done yet. So I will run this IntelliJ IDEA. Let him run. And it runs, I will say, the device manager. So device manager. Yep. We will see that this machine actually is it's Tesla K80. It's an awesome machine, I would say. It's an amazing machine. So, you see, our password expires today, so we're just on time. So, what I've done, I'm an enterprise person. I work for Deutsche Telekom. This is a bloody enterprise, pure enterprise. So, I have created a small program, which is an enterprise program, which is running on Tommy. So it's a pure Tommy, but does something very fancy for us. It runs some stuff on the GPU. I'll just make a small demo. I sincerely hope it's going to work. So since we have this Nvidia stuff there, I've run it on pure CUDA for our project. Please run. Once again, please connect. So if you're not hurry enough, oh yes, it's running. If you are not in a hurry for the lunch, I hope you're gonna like this demo. So now, as you see, there's somewhere in the clouds, there is this machine. Oh, actually, they finally have provided this copy to clipboard button. And we are running on port 8080, of course, because it's a Tommy server. It's, I guess, GPU.CUDA -1. And let us see. If it works, it now connects somewhere in the... Ta-da! We have created a very, very GPU-like stuff somewhere in the clouds, in Northern Ireland, I guess, and made it as an enterprise app because it's a Tommy running GPU CUDA inside. It's doing this wonderful, beautiful Julia fractal for us. So I think it's an interesting, oh, of course, it's not running anymore. It's a very interesting way to combine our things. So once again, you see most of the providers are now doing this, so you can, but only within Nvidia, since AMD is inside. We want to do another weird stuff, a little bit crazy stuff, I would say. How many of you know the JavaScript engine? And you know that Java 9 syntax now is very JavaScript-ish. So why don't we copy-paste this program to a JavaScript file? And if you see here, I'm not sure if you're able to see here, but I do my best to show it. We will run a JJS program. Oh, let me just first show it to you. So cut JSCL program. You see this is a JavaScript program. You see these vars, you see these functions, like, you see this kernel. And if we run it from JavaScript, we get a JavaScript program which uses a JVM to run a GPU stuff over it. Crazy. I enjoy doing crazy stuff. Applause. Yes. Yes, but finally, I would just say, as an example, so for that project we were using, stock markets. I'm not sure if minutes left, by the way. Example. So if I run it, that's a very simplified version of what we have done. It should be fast, I guess, but that's Java EE. You have some time to warm up. If I go here, now please work. For the demo gods, it's always not working, but I hope it works. We draw histograms, special histograms, and since histogram is a task for a GPU, it's a very common task for a GPU, we said, okay, why do we load processors if we have GPU for that? Oh yes, it's not showing up, but I guess oh yes. So now if we click at the stocks, it draws some histogram. And it's just filled with random data. But you see, this is a pure enterprise application. And if we go to the stuff, we see that the kernel times for all of these computations are less than a millisecond, actually. So to draw a histogram, which is a very GPU task, I would say, we have a wonderful, combination of Java running GeoGL and producing us these histograms. So as a result, we actually reduce the CPU usage up to 70% for this kind of project. So instead of running it on a 50 machine, only pay for 5 machines with GPUs. And as a result, we get a cost reduction. So the CPU usage was really lower for this project. So as a result, it is here. You see for Nvidia, this is now 1080. You receive 2560 stupid processors, but there are a bunch of them. For AMD, you receive 2300. AMD APU, the idea of combining all these memories which can be used together, you know, almost half of the processor is array. Even on this machine, which is one of the latest Macs, almost 1/3 of the processor is a built-in Nvidia, not Nvidia, but Intel processor, Intel graphics processor. So you're able to use it. And even on smaller devices, like like your mobile phones, you still have an array of devices which can be run by a CUDA. But before trying to use them, as you saw, it is hard. Please read these 2 books. These are good. These are nice. And if the task is suitable, use it. It's hard, but it's worth it. So, well, thank you very much for your attention. So, I'm quite recognizable. If you have questions and you don't want to eat, ask me.